Alright, silly people, here's the situation. We are just trying to obtain the differential equation for a rocket's velocity as a function of its mass, um, given there by Goldstein, um, for a rocket ship that's traveling at a relativistic speed. Um, and then finding that you can rewrite the equation in this uh, form of beta here. Uh, So this is a pretty interesting problem, and it references exercise 13 because it starts the same way. Uh, you're starting with the differential of momentum, which is going to be the momentum at a time after t plus dt minus the momentum at time t. Um, in special relativity, momentum is given by, or the scalar version of momentum is just given by m gamma u. Um, but there's a lot more at play here because we're also considering the momentum of the exhaust particles. So let me write out what the whole differential is going to be. Uh, m minus dm u plus du, that's the momentum of the rocket afterwards, and then plus change in mass, and then on the inside we have the speed of the rocket plus gamma times a. The a has to have a Lorentz factor applied to it because we're solving the problem all in the same reference plane, or all in the same reference frame, and a happens to be the velocity of the exhaust gases relative to the rocket. Um, so you throw a Lorentz factor on there, and so everything matches in the reference frame, and then minus m. Actually, this is mu, which is m gamma v. Yeah, okay. I'm just gonna write it as mu here. Um, so we can just FOIL these guys. So mu plus m du, gross, m du minus u dm minus du dm plus u dm plus gamma a du minus mu. So we're going to have some stuff cancel out and stuff that we can say is negligible. So mu cancels out mu, udm cancels out udm. This goes away because it's a differential times a differential. So second order and differential change uh, says that that will tend towards zero. So we have dp is equal to m du plus gamma a du, or dm actually, it's supposed to be an m there, dm. We can just divide each of these elements of the equation by dm, the mass differential, so m du dm plus gamma a. Now, dp dm is an interesting quantity that is zero, um, because when you apply the chain rule to it, you notice that it's just dp d tau dm, and it doesn't matter what d tau dm is because this is zero. Remember, this is a world momentum, and conservation of world momentum is going to imply that dp d tau is equal to zero. So we have zero on one of the sides of this equation. We have zero equals m du dm plus gamma A. We almost have it in the right form and everything. Um, but we have to do a nasty um, differentiation, which is du dm. Uh, in special relativity, u is just gamma v, but gamma is not a constant. It's also going to have a derivative. So du dm is going to be v d gamma dm plus gamma dv dm, product rule there. Um, we can also put d gamma dm in terms of dv dm. So let's do that. So d gamma dm, uh, gamma being 1 over the square root of 1 minus v squared over c squared. So it's going to be the partial derivative of gamma with respect to v times dv dm, which is going to be, so it's minus 1/2 on the bottom, but then we're also going to be multiplying by a 2v over, minus 2v over c squared. So it's truly just going to be v over 1 minus v squared over c squared to the 3/2, and I think there's supposed to be a c squared on the bottom as well. C squared there. Looks good to me. Let's just plug this in then to the derivative of u. So it's going to be v squared over c squared. This is pretty much just gamma cubed. So it's v squared over c squared gamma cubed plus gamma dv dm. And both of these are multiplied by dv dm, actually. Yeah. Okay. So that quantity inside the parentheses can be simplified because we can notice that v squared over c squared is just beta squared. So we have beta squared plus 1 times gamma, or b squared gamma squared plus 1 times gamma on the outside. I'm just taking this guy. I'm just going to look at this guy. Let's expand it into what we know what gamma is. It's just 1 minus beta squared outside. On the inside, we'll have beta squared divided by 1 minus beta squared plus 1. That's going to be root 1 minus beta squared. We can multiply 1 by 1. So the things have the same denominator, so 1 minus beta squared plus 1 minus beta squared over 1 minus beta squared. And look at that. The beta squareds in the numerators cancel out. So we'll have 1 over root 1 minus beta squared times 1 over 1 minus beta squared. That's gamma squared. That's gamma. So this is going to be gamma to the third. It's pretty ridiculous, if I'm honest, but it works. So now we know that du dm is just gamma cubed dv dm. Plugging that back into our differential equation from way back when, we just have 0 is equal to m gamma cubed dv dm plus a gamma a. To make it look more like what Goldstein prescribed, we'll just divide everything by gamma cubed. So we'll have m dv dm plus a gamma minus 2. And you know that gamma to the minus 2 will just be 1 minus b squared over c squared. So we got there in the end. This is what Goldstein was looking for. It's going to involve some integration. Remember, we want this crazy form of beta that Goldstein provided, which I'm going to copy and move down here. Missed a parent. Okay. So let's just go ahead and, well, first I'm going to divide everything by m in this equation. So it's going to be 0 equals dv dm plus a over m 1 minus v squared over c squared. And then solve it so that we have minus a over m 1 minus v squared over c squared equals dv dm. And then rearrange these guys so that we have minus a over m. We have dm on this side equals 1 over 1 minus v squared over c squared dv. This is where the integration is going to come in. So you can probably already see that the left side is going to be a natural log. So we have minus a. This is a subtle point. M naught is actually less than m because, wait, no, m naught is actually larger than m, right? Because you're starting with a rocket. It's going to have a lot of fuel, but as it goes, it's going to lose that fuel, so it's going to lose mass. So we're really integrating from m naught over to m for dm over m. On the right hand side, I'm going to multiply everything by c squared, top and bottom. So we'll have 1 over c squared minus v squared dv. So I'm going to, on the left hand side, I'm going to actually flip the integration bounds by distributing the minus sign. On the right hand side, I'm going to go ahead and just do this integral. This integral is of a defined form. So it's going to be, I think it's going to be c over 2. No, 2 over c. My bad. 2 over c natural log. And on the top, we'll have c minus v. Bottom will have c plus v. That's the definition of that's a textbook integral that I just used from the table. You could probably derive it if you wanted to, but I just skipped to the end there. I'm going to integrate the left-hand side. That's going to be natural log of m divided by m naught. on the right hand side, I'm going to simplify to 2c natural log c minus v, c plus v. Is that right? Maybe this is 1 over 2c. So this could be c over 2. Okay, yeah. Yes, okay, now you can see that now that we have both of these uh, sides of the equation are natural logs, you can probably infer that our next step is going to be raising both of these guys to the e factor. When we raise both of these guys to the e, we're actually going to have m over m naught to the 2a over c on the left hand side. On the right hand, we'll have c minus v over c plus v. Okay. We're looking for beta, so we have to, on the right hand side, let's just go ahead and divide it by 1 over c on top and bottom. So it's going to be 1 minus beta over 1 plus beta. Let's distribute this guy on the right, so we'll have 1 plus, we'll have m over m naught plus beta m over m naught 2a over c 2a over c is equal to 1 minus beta. We'll look at just what's in terms of beta, which is going to be m over m naught 2a over c plus 1 on this side is equal to 1 minus m over m naught 2ac on the other side. And then we just divide everything. So on the right hand side, we'll have 1 minus m over m naught 2a over c, 1 plus m over m naught 2a over c. Is that right? Ooh, it's right. So it took a few things to get here, some physics facts and some table integrals, but we got there in the end.